about clustering algorithms. We're going to talk something which is a much more annoying problem in clustering. And at the end of the lecture, I will be happy to tell you we will not have any answers to this problem. But we'll have a number of possible ways of going about doing it. So, now we've seen K center, K median, K means, and we've seen spectral, which is basically what plus C plus K means, right? Some magic tricks plus K means. And of course, we've mentioned this issue before, but we haven't really spent much time on it. This magic number K keeps showing up. And we've only seen one way so far of trying to get around this issue of choosing K. That's what. Namely, with hierarchical clustering, we said we're going to solve the problem of choosing K by not choosing K, right? By just choosing all K, and then seeing what you get in the process. So hierarchical clustering is a way to not choose K at all. But of course, this is not particular. This is definitely one useful way of dealing with data when you want to interact with it. But there are often times when you do expect that there is some right number of clusters, and what you need to do is find it. And this is probably the biggest problem in clustering, and it's not even a problem of clustering in some sense. It's a problem of what is called model selection. So I don't know if you've heard of model selection. This transcends beyond clustering altogether. So there's one way of thinking about this is called the model selection problem, and I'll explain what this thing means. One way of thinking about this is what is called the bias variance problem, which is related. Another term that often gets thrown around is Occam's razor. Maybe you've heard of this. These are all references for the same underlying question, that what you're trying to do is fit some model to your data. And again, like I said, this is at some level this has nothing to do with clustering. This is a very basic problem in any kind of data situation. You're trying to fit some model to your data, and there's a kind of spectrum of choices here. You can make the model very precise, or you can make the model very crude. And the problem of how to choose the right model is the problem of model selection. For clustering, of course, at least in the most basic setting, once you've chosen your features, you've chosen your geometry, the only parameter you have left to play with is the number of clusters itself. So in some sense, for clustering, model selection is choosing K. In general, this may not be the case, right? For example, when you're doing density estimation, right? You're trying to find a collection of Gaussians, right? So there's of course K, but there's also the means of the Gaussians and the variances. And so density estimation you can think of as a kind of model selection problem. Except that there you have tools to help you actually select the model. You have some kind of way of saying your models are good or bad. And in general, you may not have it. So that's why model selection is a larger sort of thing, and there are many solutions to this problem. The bias variance issue is actually an interesting problem because it gets to the heart of why these things are tricky, right? And why this is a big problem. How many of you heard of bias variance problems? One. Okay. So do you want to start off using what?
So let's suppose, so basically it means like high variance means the model overfits the data basically. And
high variance means the model, is that correct?
I mean, if you take a machine learning example, let's suppose
high variance should be underfit.
Underfit?
Okay, go on.
So let's suppose you do you have a problem where you find basically the logistic regression, let's suppose.
Yeah.
And you add a regularizer with it, and so there's a parameter which is basically it's a trade-off parameter, which is basically trade-off between the bias.
Right. So you're giving me a solution to the bias variance problem.
Yes.
I want to tell you the problem.
I'll come into the problem.
Yeah.
So if you basically, it depends the objective. So the objective is to minimize things. If the objective is to minimize that thing, so if the value of that particular parameter is very high, so it is basically assigning more weights to the less weights to the parameter because the value is high.
Okay.
Okay, because the objective is to minimize things here, so it will assign less weight to the parameters. And if it assigns less weight to the parameter, then it's high bias basically, and it underfits basically this.
I see what you
right?
Okay.
It's underfitting the data. And when the value of this parameter is small, the variance will be high because now you are giving more weights to the parameters.
Okay. I haven't heard this version of this explanation, so I'm trying to parse it in my head to translate it to what I'm normally used to thinking about. But I see what you're saying about that. Let me try to sort of give another, and I should say that I've thought about bias and variance for, it's taken me a while to get my head around it, so it's not, it's a confusing notion. So the way I like to think about the bias variance problem and maybe how it relates to model selection is in this following simple example. So in any kind of learning problem, right, you have some data which is usually drawn from a population. So you have the population, right? So you have some population here, and you draw samples from it. What you're hoping for is that the samples somehow represent the population in some way, that they capture all the interesting aspects of the population, its distribution, its modes, its density, its variance, all of that. And so you hope, therefore, that if you can fit some kind of descriptor, some kind of model, right? So you take this and you build some kind of model, and if you fit some model to this data, this model is correct or is accurate to describe the population. And this is where the problem comes in. That in some sense, there is error in getting samples from the population because there's statistical variation. And then there is error in fitting the data to fitting a model to the data. And you can trade off these things, but there's, you're going to pay one way or the other. So let's take an example, right? So suppose I have some points, right? And I want to fit a model to these points. I could say that my model is some kind of linear regression, right? So I might say, okay, the best fit for this would be something like this. I might say, no, I can actually fit a spline to this thing. A spline is going to be a good fit for this, and maybe I'll be able to go straight across like this. So obviously, as your model gets more and more sophisticated, you are better able to fit the data that you are actually given. Right? The higher the degree of the polynomial used to fit this data, the better it'll fit. If you have n points, you have an nth degree polynomial, you'll fit it exactly. Right? So as the model complexity increases, so as model complexity increases, the fit to the data increases. Right? Okay. So as always, there has to be a catch here because you can't just keep making it better and better. There's a catch, and the catch, of course, is that. Well, what's the catch? What's wrong with this? Use a model, I get a better fit. That's why I wanted a fit, right? I'm getting a fit. Is there a problem with this?
Yes.
Yes. So you think there's a problem with it because you just told me about Biasvariance. Can someone else tell me why there might be a problem with this? Why would this be a bad thing?
Overfitting.
Sorry?
For future data, is you get model not just to fit the data you get, it's the prediction for the future data. If you overfit, then the future data might not fit this model.
Exactly. That basically, if I spend a lot of time optimizing this data is an imperfect representation of the population. So tomorrow I get another sample from the same population, and maybe it looks something like this. Right? And in order to fit my data correctly now with this high complexity model, my model changes a lot. So every day my model changes. So if every day your model is changing, then in some sense you haven't learned it. You're just changing your answer every time you get something new. You haven't come up with any kind of general rule that should be able to predict data. Another way of saying this is that this model will predict very badly on the other data, which is the way I think you were framing the thing, right? Because you've optimized it so carefully to today's data, it will probably not do very well in tomorrow's data. And this defeats the purpose, because the goal in many ways of modeling is not just to explain what you've seen, but to predict what you haven't yet seen. And these are both sort of competing criteria. And so, by being more sort of jittery in some sense, more sensitive to small changes of data, You can fit your current data better, but you fit the other data worse. In other words, your variance increases. Right? But overfitting increases your variance because every time a new sample comes in, your answer should change completely. And that basically is a high variance problem. Okay, so this is basically the high variance scenario. Okay, so, well, okay, increasing model complexity is a bad thing. Bad modeler. Let's reduce model complexity. Let's always use straight lines to capture my data. You have a question?
They are dealing with real world data, it doesn't matter what model it is, it always changes.
It always changes. So you're saying we can never know anything. This is a somewhat interesting and nihilistic view of knowledge. I mean, you're basically saying that by this argument we should never be able to do any predictions because we can never know. Is that what you're saying?
Yeah.
Ah, interesting. I didn't expect in the data mining type class you would argue that we shouldn't predict anything, but this is good. Okay, so what should we do then?
I don't know. Even if it's a complex model or a simpler model.
So okay, let me ask you this: why do you want to learn about clustering?
Yeah, we are trying to basically build a model that fits some data.
But there's no point.
Why choose a complicated model? Because this is a linear classifier.
Ah, so your argument appears to be, we're going to be confused anyway, so let's keep it simple. Is that what you're arguing?
Yeah.
Okay, that's actually a reasonable argument. An argument a lot of people make. I mean, it's very popular in places like Google to say, keep the models very simple, and because, why try to complicate things? But we'll get back to your point. We're going to get back to it very soon. But so this is not as anarchist as I thought it was going to be. So yeah, it's good. So let's in fact, yes, let's decrease the model complexity. Let's use linear classifiers, linear regression for everything. Nothing wrong with that. So let me draw my picture again. So now I have my picture. I have my points, which again kind of look like this. And I am only going to do linear models. Okay? Whenever my data comes in, we use a linear model. So linear models, you can think of them as more sluggish, right? Because they're lower model complexity, they don't change so much. They're kind of lazy. So when new data comes in, it might change a little bit, but they won't change very much. So we've solved the variance problem. They are not going to have high variance. Is there any problem with them? Sorry?
Yeah.
What's the problem with them? I mean, maybe there's no problem. That's why we should always use linear classifiers. But is there a problem?
They're not as good at predicting.
Why not?
I mean, if maybe there's a better model for the data than linear. What if you have some kind of parabolic function, or what makes a linear classifier better than? Your data could have some other underlying structure that's different than linear, and if you had chosen that classifier or learned to use that classifier, then it would be a better fit than the linear.
The problem with fixing a simple model is that unless your data is generated by that simple model, you're going to have problems. So this, in some sense, is now. So you can think of this high variance as coming from uncertainty in how you sample from the population, and having to account for that. You can think of bias as uncertainty in terms of how your model is capturing, your set of models is capturing the population itself. Okay? Now, I came up with this diagram about 10 seconds ago, so I won't take this that seriously. But this is why these two things are somewhat different, but they trade off against each other. In other words, if you fix your set of models that you want to use to describe the world to be simple, you will reduce variance, but you might lose the ability to capture your data at all. And this is no longer a sampling problem. Even if you had perfect information about your world, you might not be able to capture what's going on. Right? Here you can argue it's a sampling issue. As you take more samples, you hope that you can sort of reduce variance. But you can't do that here. You are intrinsically flawed in your thinking. And this, of course, is called a bias problem. So this will have high bias. Okay? It is fundamentally shifted away from what the true value is going to be. Yes?
So you said the variance is coming because of the sampling thing.
Yes.
And why the bias is coming? Can you explain?
Because of your imperfect match between what your models describe the world to be and what it actually is.
Okay.
So this is not even a statistical score problem, it's a modeling problem.
Okay, you said my model is linear,
right?
But
Or
my-
the class of models I'm willing to consider as linear,
Okay.
that is not expressive enough to capture the world of a
Okay.
model. That's why it's not a sampling issue. It's not a statistical problem. It's a modeling problem.
Yep.
Variance is a statistical problem. So the bias variance trade-off is basically, again, in some sense, it's more than that, but it's also a model complexity issue. That as your model complexity, so you can think of model complexity along an axis here. Right? On one end you have high variance when model complexity increases. And one end you have high bias when the model complexity decreases. And a lot of work in sort of doing bias variance balances to figure out optimal points. Minimizing mean squared error is one way of minimizing bias and variance. So for example, we can, how do we, let's see. Okay, so the variance of a random variable can be written as someone.
Even x minus mu whole
Expectation.
square. Or
Expected value of x squared
Minus.
minus the expected value of x whole squared. Yes? Right? Where am I going with this? Okay. So the expected value of x squared is equal to the variance plus the mean squared. Okay? So in a crude sense, if you're trying to minimize mean squared error, you're minimizing some kind of sum of bias and variance. Is what's going on here. The expectation is capturing your bias, and the variance, of course, is the variance. So that's where this sort of thing comes from, that you want to minimize this, so you can sort of, you're trading off these parameters. One goes up, the other one goes down, right, if this is kept fixed. And that's where this bias variance, in a formal way this way. Okay.
So this is the variance plus the mean square.
Mean squared, yeah. So I mean, so this is not. Don't think of this as a rigorous argument, but there's a way to make this more precise. That basically, you think of that as your kind of error, right? That the bias is basically your expected difference from the mean,
Okay. Yes.
and how much you're shifted from the mean, right? From the true mean of the population. And so you can,
Okay.
in spirit, this is. So for clustering, right? What is the equivalent of the bias variance problem? If you translate bias variance into clustering problems, what is it? The language, yeah.
Well, I guess that's easy to answer if your data is labeled, right? Because if your data is
Okay.
labeled, then it's just whatever it should be.
Right. What I guess what I'm asking is what is the notion of, how do you translate the notions of bias and variance or model complexity into a clustering problem? A simple, like the K-means. What do these things correspond to is my question.
Spread of the cluster?
Sorry?
Spreadness of the cluster?
Yeah, in a sense, the variance in fact corresponds to the variance of total variance of the clusters, which is basically so for any cluster, it's the expected, in this case, if we're doing this cluster, right, you can just equate it to the sum, right? So the variance is basically the sum over all x, sum over all x belonging to Ci, the distance between x and mu I squared. So it's basically the actual cost of the clustering. That's your variance. Right? The bias here, so high bias, low model complexity, is captured in terms of K. Right? So right. So the number of clusters is basically a proxy for your bias term. Right? This is your bias term here. This is your variance term here. So in clustering, if you want to, and so does this trade-off make sense? So let's try to analyze this trade-off and see what happens. What happens if your model? Yeah. So this I've got something wrong here.
What if you don't need to specify the number of clusters?
One second. But that's what this lecture is about. If you had come enough time, you'd have seen. So, okay, I've got something wrong here because if I say variance of the cost, as I increase the model complexity, the cost goes down. So this is not quite that. But, hold on, let me- I mean, in a sense, it is correct, because if you take another set of points, you have a completely different cluster. If you take another set of points, you have a completely different clustering again. So while this analogy is not quite working mathematically, it is correct that as the model complexity increases, as k increases, your clustering kind of jumps around too much with your data. And as you reduce the complexity of your model, you use like 1 or 2 clusters, then your model doesn't change very much, but its skew is very high. It's very far away from the true solution you're looking at, right? And we know that if you increase the number of clusters up to n, you can get 0 error, and of course you don't want that, because it doesn't capture anything. And if you reduce the number of clusters to 1, everything gets put in one bucket. It has low model complexity, but it doesn't really capture anything interesting. So in other words, the bias variance or model selection trade-off for clustering is really about how to pick the number of clusters when you want to find it. And again, this goes back to Occam's razor, right? This old sort of hairy principle from the 14th century that says essentially that you want as simple an explanation as possible. Now, this does not mean you want the simplest explanation. You want the simplest explanation as possible. And that's where the trade-off comes in. The as possible part is, as long as you're still able to predict or do what you have to do. A simple one is better than a more complicated. And a lot of the work in model selection ultimately boils down to this philosophical principle that you want to reduce model complexity as much as possible. All else things being better, a simple model is better than a more complex one. And this goes exactly to your point. And if we're not quite sure about the world anyway, let's not throw in extra assumptions about what's happening. Let's keep it as simple as possible. All right. So how do we do this then? So what are the different ways in which we can try to handle model complexity and try to manage this problem of trading off model complexity versus quality of the prediction for clustering? So perhaps the oldest method, and the one that sort of has stuck around longer than it ever was reasonable for it to stick around for, is something called the elbow method, which is such a shocking hack that you will be just impressed. So the elbow method is basically the following idea. I mean, I think it was a clever idea when it first came out, but it's an interesting hack. So what you do is, if you want to figure out what seems to be the right number of clusters for your data, you make a plot. So you plot the following. So now on the x-axis you say, this is the number of clusters. Okay. On the y-axis, you plot the error. Well, not the error. Let me say the cost of the clustering. Okay, so for k-means, it's the average sum of squared distances. So if you start plotting this and you increase k, what is this curve going to look like?
It's cost decrease.
Right?
Decrease, cost decrease.
Right. So does it decrease? And so might it decrease like this?
I know how the curve looks like.
How does the curve look like? Does it look like that?
No.
What does it look like? What's such a curve called?
I mean, the convex.
So what generally happens, and for many problems you can prove that this is true in fact. What you're going to see is some kind of convex curve. You're going to see, well, or at least discretely convex curve. You're going to see points that look like this. So let me at least convince you that these 2 points make sense, right? If you have one cluster, you're going to have lots of error. If you have n clusters, you're going to have very little error. So this kind of, you do expect this kind of decreasing behavior. And it turns out that this has this kind of curve design. And let me, since these are discrete, let me not actually try to pretend that this is going to be a smooth curve. In fact, that's going to be important here. So let me just do this. It goes down like this, it goes down like this. Okay. So the elbow method basically says, look at this plot, mumble some magic words, and pick this as your right answer. Because that is the elbow. It's the point at which it appears to be the case that increasing model complexity is giving you diminishing returns. Another way of thinking about this, that if people have tried to make this a bit more precise, since you can't go and ask Robert Thorndike, the inventor of the elbow method, every time you want to do a clustering. what he thinks of the elbow, is to say, well, look at the point where the slope goes from this side, this is I think -1 to below -1, or to below, above -1. So it's going minus large and it's going large. Because the -1 is the exact point at which, so if you're saying that d cost by dk is equal to -1, right? Suppose you're looking at this point. Then what you're saying that approximately delta c is equal to minus delta k, right? So what you're saying is that the benefit you get from reducing the error cost of the clustering is being paid for exactly by the increase in the model complexity. And if you go any further, it's no longer getting paid. You have to pay more in model complexity to get a lesser and lesser improvement in the cost. And so it's basically a diminishing returns argument. Keep increasing the model till it no longer is beneficial to do so. This is the elbow method. You'd be surprised how many papers basically do some very nicely. Still.
What if you don't?
Yes.
What if I just have a line?
Very good question. That's a good question. What happens if you have a line? You
Any of
have
them.
no elbow. Basically, your arm is paralyzed or something.
Or if you have a simple curve.
What would this mean if your data looked like that? What would that I would argue that says something about your
I know
data,
what
in
it
fact.
means. If you have a bug in your code.
And once you have Clement come and fix your code for you, then what does it mean? What do you think that would mean if your graph looked like that?
It's uniform points.
So tell me, explain that some more. I mean, you have some thoughts in your head. Tell me why you think it's uniform.
If you like put some grid, it will be every cell.
So what you're saying, suppose your data looks something like this. I mean, maybe it's not a good grid, but it's kind of almost even. That's what you're saying?
Yeah.
So why do you think that kind of data would generate that kind of curve?
Because, somehow should be linear, right?
Sorry?
Somehow should be linear as the.
And I'm asking for a formal argument. I'm asking for intuition. Why do you think that? So how many of you would agree with the sense that this should give you that? Yeah?
I mean, it seems like, so if we look at the one extreme where we have the number of, so every point, so we have like none, and then if we look at the other extreme where it's all of them, and then as you reduce it, like, I take from the whole set down to another one, the distance between all the points, it should capture kind of an even amount of information at each time I add a new cluster, right? Because they're all evenly distributed. So if it captures the same amount at each step, each time I break it into discrete points, then it should be behaving linearly. The cost should move in the same direction.
So maybe one way to think about this is compare this data set to this one.
You're going to have some kind of jump as you move.
So the intuition here, and this again goes back to what Samira's saying, what Nick is saying, is that if you had an actual clustering of your data, a real honest to goodness clustering, then once you increase the number of clusters beyond 2, you're not going to get much improvement. I mean, you might subdivide these things any further, but the cost is not going to go down a lot at that point. You've already done the best you can by sandwiching this, and maybe this is the cost or whatever, right? I mean, you're not going to get much. You're going to get improvements, but not a lot. But the big jump is going from 1 to 2, because now you have a huge improvement. And that's the intuition behind the elbow method. That if you see bumps, non-trivial bumps, then you expect to see something non-trivial in the data. If you see no bumps, like in this example, then at every level it's kind of self-similar. At every level looks like the previous level. There's no real structure in the data. Okay. So two observations come out of this discussion we're having here. First of all, that it's not just that you're looking for an elbow. You actually have some kind of informal reference. That you can say that somehow being very far away from the reference tells you the data is more clusterable. It's a well-clustered data set. And in fact, people have used this idea to say something like, look at the distance from this point to the origin. The closer it is to the origin, the more well-clustered it is. Or look at the area under the curve. Like there are these things called rock curves, there's the AUC metrics. Obviously, the better your clustering is, the lesser the area under this curve. And if you reparameterize, it becomes more. So it depends on which way you explain the AUC. But the idea is that this area should be very small, right? In an ideal world, right, what's going to happen? In an ideal world, you have some data, and let's say it's perfectly clusterable at k clusters, right? At k clusters, its cost is 0, and before that, it's not, right? Because you have to. So what you're going to see is you're going to see some. You're going to see maybe some decreasing cost here, right? And then there's going to drop like a stone to k, and then it's going to go like this. So in the limit, you have something that's structure looks like this, and this gets really, really small. Because if everything was in one cluster, then this would snap all the way. So as your clustering gets tighter and tighter, the amount of area under this reduces further and further. So that's one thing you're seeing from this. The other thing that you might see, which is a problem in fact, is that there's no reason to have only one elbow. And again, I've drawn this data set before, right? So suppose our data set looks like this. So it looks like this, and I'm going to make this very vague. But if you zoom in on any one of these clusters, right, it looks like this. So this is one big cluster. But when you zoom in on it, it looks like this. So now you should see a bump at this, but you should also see further bumps at this. So in fact, you will see curves that look like this. You might see one elbow like that. You might see another elbow like that. Then you might see those. So now if you have two elbows like this, which one do you pick? It's not clear. So the elbow method is all right, all well and good. And it does have some sense of it captures sort of bumps in your data, things where things collapse very quickly. But as you can see, it's very imprecise. It's all in the eyes of the beholder, where you have to look at it, and that's not very satisfying.
And the way the cost function is derived, I don't know, not the cost, like the complexity, the model complexity.
Yeah.
It should be both. You should consider all the parameters and give you the output. Not that given a parameter, I give you an output. In other words, I want to have in model complexity, I want to have k as well. So this is called bias, and I want to have a variance, and both of these things give me an estimation of the model. And then I want to add that's how it should be. You see what I'm saying?
No.
So you have two terms in your cost function. One is regarding your k bias, and the one is regarding your variance. And you somehow
Yeah, but that's not it here, right?
No, that's not here. That's what I'm saying.
No, there are. Why not? This is the cost of the clustering.
No.
This is the number of clusters.
No.
Why not?
Because it says given a cluster, I give you the cost. I give you the cost of clustering.
Yeah.
Given a k, I give you a cost of clustering.
Because all my algorithms are for a fixed k.
Yeah, but you don't know what's the k.
That's what I'm saying. This is a method to find the right k, given that you have an oracle that for a fixed k would give you a best clustering.
Yeah, but you don't know how well should you, how much emphasis do you need to put into the k?
So what you're saying is we don't know how to weigh these parameters
Yes,
against each other.
yeah, you need to
Okay,
weigh.
so your question now, let me rephrase. What you're saying is how do we know how to weigh these parameters against each other?
That's what I was explaining, that you need two terms, that let's say you
Okay,
sum them.
let me
you
answer the
weigh
question, since you asked. The question of how you weigh these parameters against each other is actually a good question, because you could imagine that if I were to stretch out this curve by scaling k up, my elbow would disappear or become very pronounced. And that's very arbitrary. And there's no reason why there's no reason why my elbow should be a function of scaling parameters on these model complexity terms. And this is again another problem, right? So one way that people have looked at this question is to say, rather than trying to find the best clustering for a fixed k, we will try to optimize some generic cost function
Yes.
of the combination of parameters. And the thing we're going to do is something like this. The new cost of a clustering is equal to the old cost of the clustering plus some lambda times the number of clusters. Okay? This cost function has a name. This problem has a name. It's called facility location. And these two the problems of facility location and k-median clustering are very closely related. You can use tools for one to solve for the other. The idea of facility location is there's a whole story around this. And the idea is that you want to build these sort of post offices to serve your clientele, right? And of course, the more post offices you build, the closer the response time, or the closer the less amount of travel your postmen have to do, and the less amount of gas you have to pay for. But building a post office costs money. Building a post office in particular costs a lambda amount of money. And paying for the gas costs this much amount of money. So now you have some kind of combined cost function. And so you want to choose where to put your facilities and how many of them to put up, so that you can balance this overall cost. Right? So this is like you can think of this as a Lagrangian relaxation of K clustering, if you know what Lagrangian relaxations are. If you don't worry about it. But if you do, you'll see that this is basically a constraint, and then you make the constraint soft by adding a lambda. This is the Lagrange parameter for that. And you can optimize this. So this is great. We have a smooth cost function now that captures both things, except for one tiny little problem. What's the tiny little problem here? So now I'm going to minimize this.
Well, you don't know in what direction of C to go.
C?
Yeah, C is the clustering, right?
What's the direction of C?
Yeah, well, delta C, whatever. You have some given, you have a clustering, and you
But I have a cost function. I just minimize this cost function. This is my cost function. Find C to minimize this cost function.
Yeah, how do you do that?
That's a minimization. I have to do some minimization. I write some optimization. I run my, build my convex program, do whatever. That's not the problem. There's another problem
How to
here.
choose our lambda?
Yes. How do you choose lambda? I have replaced one parameter I don't like, k, by another parameter, lambda, which is even murkier. At least k, okay, number of clusters. Lambda is some Lagrange parameter that wait. It's even harder now. So this is why this is, in some sense, a solution is not really a solution, because we just exchange one parameter for another, and we don't know what to do.
You don't estimate it from the data. You can estimate it from the data. You have your test set, you have validation, your learning set, validation set, and then you have
That is one of many ways in which you could try to figure out what would be the right lambda, and we're going to talk about that in a second. So the problem is that while we have some way of incorporating model complexity into my cost function in a way that gives me one thing to optimize, we don't know how to compare these things against each other. There doesn't appear to be a principled way to weigh these things against each other. And they're almost the wrong units as well, right? One is, if you're thinking of clustering in space, this is basically distance squared, some kind of miles squared, and this is a cardinality. They're not even compatible with each other, right? I mean, this could blow this out of the water. I mean, for example, think of what happens if you put lambda equal to infinity. Then all you're going to do is make sure everything's on one cluster. If you put lambda equal to 0, you're going back to normal clustering. In fact, you just put everything in a cluster by itself. So lambda does give you a way to smoothly vary k, but you have to know how important it is. Right? So you've gone from just not knowing what to do with k to have some smooth way of varying it, but not knowing exactly how to weigh this parameter. So that's where we get into the whole sort of alphabet soup of techniques that people have tried to come up with to basically figure out what lambda is, how to weigh these parameters. And they're all based on some assumptions about what the underlying model for the data is. And based on that, you can express lambda as terms. Okay? Yes?
Can you write another function?
I can write any functions.
Yeah, so,
I like sines personally.
sorry?
I like sine functions, like cosines.
Yeah,
Which function?
So can we, so let's say model of clustering. Can we write another one? Model of clustering. Just model complexity of a given clustering
Yes.
is equals lambda 1 times k plus lambda 2 times the variance.
You mean a cost function, another cost
Yes.
function? How is it different?
It's different.
No, it's not.
No, lambda 1 times the variance.
Yeah, so this is essentially a variance term. The distance, the error.
Cost is the variance.
The error, the distance, this thing.
Oh, okay, so then it's the same.
The same.
Okay, cost is then basically the variance, the error.
I just put as cost because maybe you're not using k-means, you're using something else. Right, this is more general.
Sure. That's
So one question. So whenever you have a Lagrangian and you try to minimize something, right, and then so at the time of minimization you differentiate and you find the values of lambda basically, which are the Lagrangian parameter, right?
That's
Fine.
when what you want to do is to solve this problem
Yes.
with this hard constraint.
Yeah. If the k is fixed, then.
Right.
Yes.
For a K, that's right.
Yeah.
And in fact, that's why you can use facility location to solve K-median.
Mhm.
So that I didn't go into this, but there are a number of more sophisticated algorithms for solving K-median that basically go by Lagrange relaxation. You Lagrange relax it, get, oh, it's facility location. Solve the facility location, and then do exactly what you said to find the right value of lambda to optimize for. Yeah. So yes, this does happen. But again, we're not trying to do that here. Here we actually want this to be a smooth parameter to play with.
Because when you said like we cannot find the value of lambda because lambda is again a free parameter here because we don't know.
Right. You can find the lambda
Yeah.
if you want to know a fixed K.
Yes, for a fixed k.
Right. What we're trying to do here is get a bit more general about this. That somehow we want this lambda to capture some more general way of relating model complexity and error. And we're going to see how to do that. Yeah. So this brings us to what are called the information criteria, and there's a whole collection of them. The first one is the most well known. It's called and in all of these, I'll explain the first one, but in all of these, the basic idea is that what you want to do is express this more generally in terms of some kind of model complexity based on some underlying model you believe the data to have come from. Okay. And then use log likelihood to try and minimize what you do, maximize the log likelihood of it. So you basically want to do a log likelihood, an MLE type thing, and then use that to figure out the right value. So they will all come with some kind of underlying assumption. Right? So they're not going to be completely free from model assumptions here. But they give you a form of an expression that works. So in some sense, we use k-means all the time, right? But we've seen before that k-means, the form of the k-means cost function comes from a kind of Gaussian assumption about the data. That doesn't mean you can't use k-means when your data is not Gaussian, but you have to keep this in mind. Similarly, what we'll get at the end of this is a criteria that you can use generically for a clustering problem. But its intuition comes from a Gaussian type view of the world. And so you should keep that in mind. Okay? All right. So let's see. So what I'll try to do is express this abstractly, because like I said, the problem model selection goes well beyond clustering. And then I will try to explain exactly how it applies to clustering. All right. So in general, think that we have some data. So let's say some data we've sampled, endpoints, let's say they belong to RD. It doesn't matter for now, but we eventually will need to know this. And we believe they come from some kind of model, right? So let's see. So yeah. So we have a collection of models. Let's say it's M1, 2, and N. Okay? Each of which could be a viable model for describing the data. Okay? Again, if you want to think about clustering, a model would be the number of clusters. So this is the set of all. This is a set of all clusterings in one cluster. This is a set of all clusterings in two clusters. This is all other clusterings in three clusters, and so on and so forth. So that means that any model itself, MI, right, is basically some set of distributions that capture. So the set of all models with 10 clusters is a collection of choices of Gaussians that you can pick. So each model is basically some set of distributions, theta j, or some parameters theta j, about some space. Okay. Again, I'm writing this more abstractly just because I want to show you that how this whole thing derives out. So now you want to know. So y is drawn from some density function f. And here's a killer. The killer thing here is, and this is very important, is that we don't assume that f is any one of these things. So of course, for clustering, this is kind of silly, right? Because of course, your correct answer will have some number of clusters in it. But maybe it actually doesn't. Maybe there's no real good answer. That the 5 cluster solution is okay, the 6 is okay, but neither of them are quite right. In other words, for this criterion to work, you don't have to assume that you know the space the true model comes from. All you have is the models at your disposal. So you have some set of models and you want to find the best fit. So this kind of this agnostic sort of version of learning problem, right, where you don't, the true function could be completely different. You just want to find the best approximation to it from your space. Okay. And so what I'd like to do is figure out which of these models captures my data most accurately. Right? Which of these is the closest to it. Right? So you can, so let's say the true estimate is some kind of density P, some kind of function P. And there's some estimate of P based on the jth model, and we'll call it PJY. Okay, this is the estimate of the true distribution on Y if you use model G. So this is the estimate of Y based on model MG. Okay. So you want to pick one of these things. They're all going to be, plausible models of the data, and you want to pick one. And so one way to say is that, okay, there's this true model, which is P, and there's all these models you've estimated. You want to find the one that's somewhat closest to your true model. And so the way to compare one way to compare distributions is use what is called the relative entropy, or the Kullback-Leibler divergence, which says that you basically the k of P, and this is asymmetric, so I'll put this parameter here, is equal to the integral of P log P over. So P of Y log P of Y over P hat of Y dy. Okay. So again, if you haven't seen this form before, this is just a standard way to measure a distance of a kind between two distributions. Okay. If they're identical, this will be 0. And it's always positive, although it's not always. So it has some effort. Essentially, maximizing log likelihood is like minimizing the k of divergence. So if you go on here, so now you can write this out, which is equal to py log py, which is like a negative entropy of p, right, minus py log p hat. Now, if you want to minimize this over all p hat, right, you don't have to care about this term. Right, so you want to minimize this, you want to maximize that expression. So you want to maximize sigma, sorry, not sigma, integral of py log p hat y dy over all, let's put a j here, over all. Okay, so this is our goal. And if we believe the data is coming from one of these, that the data can be modeled by one of these densities, whatever it's actually coming from, then by maximizing this, we'll find the model that best captures this data. Okay, that's the idea. So it's like kind of an, and this is basically an expected log likelihood, right? There's an expected log likelihood of this, where the expectation is taken into respect to true distribution. And since that's the case, you feel like, okay, I should be able to estimate this by samples. I have a bunch of samples, they're assumed to be drawn from P. So I should be able to replace this by max over J of 1 over n sigma log p hat j of yi. Right? Because this essentially is a discrete approximation of the integral. If you actually are drawing your samples from the true distribution P, and you estimate this, then in the limit this will become that. You have to be a bit more precise to say, okay, how quickly the limit and what kind of limit. But for now, we'll just say, okay, this is a good estimate of that. And in fact, in expectation, this is, you would think this would be a reasonable thing. So we'll write this out in this following form. We'll call this Lj, data j. So this is the parameter associated with it, data j divided by. So this is the sum of log. This Lj. So the total likelihood function for that. Now it turns out that while this might be a good estimate, and this is if you've ever dealt with things like for example, if you want to sample the entropy of a distribution, if you want to figure out the entropy of a distribution, you take samples from it and you compute the MLE, the empirical entropy. It's actually biased. It is not, the expected value of the empirical entropy is not the actual entropy. So even though this looks like this should work, in expectation, the expected value of this is not that. Forget the knife. Okay, it's a biased estimator, in other words. And with a bit of work, you can actually show, and in fact, so I should say that this one is called the Akai-K information criteria, after the Japanese statistician who invented it. So what he showed was that you can estimate the bias of this estimator. And it's roughly, and this takes some proving, but it's something like the bias of this. So in other words, this number here, right, expected value of Lj theta j is not equal to this quantity, which we'll call the, let's call this Kj. Is not equal to Kj, right? Because it's biased. But if you do this rough approximation, you do something like this. You say that, sorry, this one. Instead, you look at the estimator Lj theta j hat divided by n minus a parameter relating to the dimension of the model, the number of parameters in the model. Okay? If you get this correction term, then this closely approximates the true value. Okay? So in other words, you have to find this bias-corrected shift to get this to work. And it kind of works.
Can I ask something?
Yes.
How did we get from the integral to 1 over n?
Because what we're saying is that, again, forget the max, we want to compute this integral. This integral is really the expected value of this quantity, right, over this distribution. So now if we sample y's, they are drawn from this distribution, right? They're already drawn from the distribution. So we just sum up those y's. Py dy is essentially p of that, and that's what gives you it. Because y itself is drawn from a biased distribution. So in other words, a value of y that occurs very often will show up more often here, and so it'll
So
correspond
why
to
did
the
we
larger.
miss it in the sum?
Pardon me?
Why didn't we have py in the sum? Or p high?
Because I'm averaging them. This is the approximation of the integral. Because I'm drawing y's from that distribution. If you want to compute the expected value of a random variable, you sort of draw a bunch of samples of the random variable and you evaluate it.
Yeah, but you need to weigh those values.
You weight it by the probability of occurring, right?
Yeah, but you just.
But when you sample, you are already that is the fact that you are sampling from that distribution.
Oh,
gives you
okay,
that.
got it. Yeah, now I understand. Yeah, you're sampling given what theta j.
Yes.
Okay.
Okay, good. No, that's a good point. So you have this estimate which claims to capture this quantity, and now you can, and now we'll define the AIC criteria for model J. So the number for a particular model J to be equal to this scale. For some reason, we like to multiply it by 2n. Don't ask me why. There's a factor 2 floating around somewhere. Again, I don't know why that happened, but eventually what you get up is this. J, theta j minus, I don't know why there's a 2 here, but anyway. This is something, this is sort of popped up. They just multiply this by 2n, and there was a 2 here that goes away. But anyway, so this is a number that you can evaluate for each model. And then take the model that gives you the biggest value of this number. Biggest? Yeah, the biggest value of this number. Okay? So what does this mean for clustering? Right, so I did this whole big shenanigans here. And the key thing is this object here. And this is where it gets interesting. Suppose we are doing k-means clustering. And so we intuitively know that k-means clustering kind of has a Gaussian assumption underneath. And you're expecting these to be kind of Gaussian. If you in fact believe that your data is Gaussian, and you have a particular model with j Gaussians that's actually describing your data, then the likelihood function for that is the log of the exp of that whole expression, right? So if you take the log of the exp minus sum of distance squared, and you take the product of all the points, you've seen this before in density estimation, what you'll end up with is this is going to be minus the cost of the clustering, minus 2dj. Okay? But what is dj? dj is the number of parameters in the jth model. The jth model has j clusters, and they're all in RD. So you need j times d parameters, because for each cluster center you have to describe d coordinates. So this is basically j times d. And you want to maximize this. So what you're minimizing then is basically you want to minimize, because you're maximizing the negative of this, the cost of C plus J times D, where J is the cluster. And now if you compare that to that, what this basically saying is that using the Akai-K information criterion and using a Gaussian underlying assumption for your data, the correct value of lambda you need is the dimension in space. So all this work gets you back to a form that we're familiar with, but it tells you what value of lambda you need. And so in practice, if you want to run the AIC, you do exactly this. You add this extra term when you do the minimization. And there are ways to cluster it.
Can I ask something?
Yeah.
So how did he show this, the second line?
Which
That when you
one?
set-
This one?
No,
No,
one,
the-
one.
This one?
Yeah, this is pretty amazing.
Yeah, this is all like stats kind of muscle power, right? I mean, you have to basically show that you have an estimate. So what you're showing here is that there's an estimator that's biased. You want to figure out the bias of the estimator.
Yeah, I understand those.
So but that's how you do it.
But so basically the idea is that it's only biased just by the dimensionality of the model
Yeah.
and by the number of points that you have.
Yeah. I mean, yeah. And I should say that
This is
while
not-
I have no idea how you get that particular form,
Yeah, exactly.
I am not all surprised that it's biased because I've come across this problem before in my own work. In the world of streaming algorithms, one question that has been people looked at for a long time was how do you estimate the entropy of a stream? And so one idea was, okay, to what extent can you sample from the stream and do something? You end up with this kind of problem that you don't get a biased estimator for it. So. And in fact, you can show that there are no good estimators for entropy at all. There are no unbiased estimators. They're all going to be biased. Yes.
There was no DJ, I mean, the dimension thing, there was no dimension thing till this point.
Yeah.
Suddenly this appears here.
Because when you look at the actual bias of this estimator, it's going to start showing up. That's where this comes from. Because remember, the model J has J times D parameters in it. That's this number here, J times D. So this is the dimension of the model. Right? That's where you can express this more abstract. Yeah, I don't know how you prove this. I mean,
But
I
until
would love to
there,
know
we
that.
haven't seen anything about the P, right? About the P or P hat.
What do you mean?
P about the distribution.
LJ is in terms of P.
Yeah, but we haven't assumed what the P is.
Correct. Up to this point, you haven't. That's right. The Akai-K information criterion is not with respect to clustering. It's a general technique
Yeah.
given a collection of models to choose the right model. For clustering, the way it's typically been used in clustering in this particular form because it's convenient that this becomes your regular cost function anyway to get it back in the form that we want.
Well, it's kind of amazing.
Yeah, it is.
I don't know anything about P. I just come up with some P hat. Sample points from it.
Right, because the trick here is that your p-hats could be terrible.
Yeah, exactly.
But all you're promising is that I get the least terrible of them. Right? So if this is your P here, and you're completely close about your data, all your P hats are sitting here, you're going to get this one, but that's all you're going to get. Right? It's like saying, I get a low rank approximation. It could be terrible, but hey, it's the best low rank approximation I can get. So the ability to use P hat to actually meaningfully interpret the data depends on how good your modeling assumptions are. But yes, it is kind of cool that even regardless of that, you can get as close as you can. It's pretty neat. Okay. Any questions? So you can imagine many ways of using this, right? You could use this to pick K, or you could use this to display different clusterings and say, okay, this is what I think of the relative importance or the relative significance of these clusterings based on this confidence number here. So there are many ways you could use this number, right? And the obvious way is just find the right value of K, but you don't have to think of that. You can think of it as a penalty term for increasing model complexity. All right. the AIC is not the only way to kind of validate or capture the idea of the right number of clusters in a data set. Another way, which is actually quite simple and has some nice guarantees behind, which I actually know about when I started looking at this topic more carefully, is, I think as Clement mentioned earlier, cross-validation. And the cross-validation idea is actually quite simple, again, to implement. So by the way, I do have notes that do a much more detailed derivation of that bias term. They involve all kinds of Taylor expansions and other things that I'm sure you love. So I will put the notes up and you can take a look at it. So here's the idea. So the algorithm, so we've seen that an algorithm based on the AIC would say optimize your either optimize the cost function directly or cluster with all values of k and then correct that term, get the AIC term for each of them and pick the best one. So it's, as an algorithm, it's relatively simple. For cross validation, again, there's a very simple algorithm. And there are variations on this, but the obvious one actually you can prove will work reasonably well. And again, the idea is you have a bunch of models. So you have models M1, MR. And then what you do is, you take a data. So let's say your data actually comes in two parts. It has two endpoints, not endpoints. So let's say the first endpoint's arbitrarily chosen, I think. So randomly, so let's say the data comes in sets Y1 to Y2n. So randomly separate them into two halves. So take any of them at random. So we'll call this D, and we'll call the rest. Okay. This will be my training data. This will be my test data. So with your training data, you find for each model, you find the best model parameters. So you have models, M1, well, let's say I'm using K1 for the parameter. So let's look at, so you find the right set of parameters, theta j, for each value, given the D. And so for each of them, you get some cost function Kj, which is basically the average log likelihood. Right? So sigma P, sigma log P yi given data G. How do you estimate? So in other words, take your data, half data which is training, use that to find the best model, in other words, find a clustering. Then use that to get a cost for the test data, which means take your new data, put it in your clustering, like say with nearest neighbors or whatever, and then figure out the cost function you get. So that's your number. Okay? What you can show then is that the true cost, right, for the model, as opposed to this estimate you're getting from building on the training and test data, by a Chernoff model. So in other words, if this is the true cost for modeling your data with this parameter, as opposed to just using the trained data, the error is very small, and you can bound this error. So in fact, if you take this model, okay, so what you do is you take the model you built, and you write down the KJ hats. These are the different costs for the different choices of model here. And then you basically just choose the best J. So find the argmax. Okay. You can prove that this is going to be close to the best model you can do. So again, you're not choosing the number of clusters per se in that sort of functional form with that Lagrange parameter. You're just saying do cross-validation. And this again is a very easy thing to do. Take your data set, divide in half, run your clustering algorithm half of it, and then test the other half. And choose the right model. And it's so simple, I'm surprised we just don't do this all the time. It's kind of very easy. And you can give precise bounds on what this epsilon is going to be. It all depends on the log likelihood function, but you can bounds. So this is yet another way to choose the right model. It's not a direct functional minimization, but it's an easy way to sort of figure out what the right model for your number clusters is. The final thing I want to mention today, which is a sort of a variation on the theme of the Akaike criterion, is what is called the Bayesian information criterion. Okay. And not surprisingly, since it's a Bayesian information criterion, the idea is that rather than saying that I have each model has good, each model is described by a collection of parameters and I don't know anything about them, you of course have a distribution. You will put a prior distribution on the parameters of a model. So each model Mj, you have some kind of distribution on the theta j. There is some kind of prior belief that this is the right model. So in other words, this would be like saying that I expect my Gaussians, I expect my centers of my distributions are Gaussians with certain mean and variance, and I could put some hyperparameters on this. That's why it's Bayesian. So you put some prior belief on this stuff. And then you work through the exact same analysis we did there, which I'm not going to do now. And it turns out you get a criterion that's very, very similar. So remember that before, we got this Akaike criterion, which is basically the Lj theta j hat minus 2dj. Yes, that was the criterion we were using, and we convert that into a clustering language here. Here, what you get is something slightly different. The BIC criterion for the jth model is the same thing as before, minus so there's an extra penalty term, right, associated with the number of points in your sample. What effectively this is doing is, as your data size increases, it's penalizing model complexity, the dimensional space, more and more. So if you have more data, you really have to be getting a good benefit to be using more clusters. The idea being that if you have more data, it's much easier to overfit in some sense with lots and lots of clusters. So you have to justify its existence by weighting. Now the Bayesian information criterion is somewhat different from the AIC in terms of its assumptions. In the AIC, you assume that you don't know anything about P. You just have some collection of models you want to fit to it and find the best one possible. In the Bayesian world, you're saying something stronger. You actually assume, no, I know the world. I have this prior in my distribution. I know what's going on. And then I want to find the best answer. Okay? And in some sense, you could, I don't want to speculate on this because I don't understand Bayesian stuff very well. But maybe that's where it's forcing you to come up with simpler models, because you actually have a stronger belief about the world. So you need to justify your increased complexity much more. You had a question?
So the BIC model, P, the prior parameters, can be anything, and this is always log n?
Yes. That is correct. In fact, if you look at the notes, basically the terms involving the prior kind of disappear in the analysis. They end up being dominated by other terms. So if you do, so your question is correct. Why did the prior disappear? The analysis makes it disappear, which is kind of bizarre.
This is like big O notation or
It's
something?
a lower order term. So it's a small O. They become small O of these parameters. So it's not even a big O. It's a small O. But it's a puzzling point, right? Why the hell does it go? And that's what makes it nice, right? This works independent of your prior. So it's kind of cool. So then, if you go to stats.stackexchange, should I use AIC, should I use BIC? The BIC tell us, the AIC tell us. But the point is that they represent different ways of thinking about what your world looks like. And they represent, of course, different ways of expressing information about your world. The AIC is more, it's not as Bayesian. So that's up to you to decide how you, but that's what they represent. And again, what you're really doing is you're carving out this kind of extra scale factor to associate with the model complexity. It just penalizes you a lot more. So BIC will force you towards simpler models. That's what effectively means. And again, when I write it this way, I just want to emphasize this has nothing to do with clustering, right? It's when you actually put in these values for a particular clustering formulation, then you start getting the forms that we've been seeing before, right? Minimize the sum of k-means or whatever it is. But this works for any kind of model selection, whether it's a regression problem or something else. There are others. I believe there's one called the the deviance information criterion. There's no CIC. I encourage you to think about it so you can have a complete picture here. There's also something called the gap statistic, which again is slightly different. There again, instead of looking at log likelihood, you look at some kind of subtraction of the expected log likelihood from your data versus the true expected log likelihood, try to minimize that. So it's slightly different. It has other pros and cons of that. And so there's a number of things like this that people have used. And they all boil down to, I will assume something about my data and use that to penalize complex models in some appropriate manner.
But in BIC, you assume something about your data.
About the work, not
About
the
the
data.
work. About the work.
Yeah.
But when you have enough data points, that completely disappears.
Which is, oh yes, yes. It's kind of weird, right? But in some sense, if you have enough data points, you don't have to assume anything about the work. The data tells you what, I don't know, it's an interesting point, yeah. Yeah, it's kind of mysterious how it just goes away.
It's very big.
Yeah. All right, any questions? So again, these are things that are useful to keep in mind as you, if the goal of this class, right, is to help you learn how to play with data and do clustering with it, understand the pros and cons of the different clustering algorithms you use. And in some sense, this lecture is really about how to navigate the space of K and what are some principal ways of trying to figure out the right value of K. The elbow method, of course, is not what I'd call a principal method, it's an ad hoc method. But that idea that comes from the elbow method can be made formal in many forms. And then you can, these are not by any means the only ways to make it formal. If I talk about information theory clustering, you'll see even other ways of doing this. But it gives you that same sense of a trade-off and how to balance trade-off based on what you normally do. Okay. All right. So if you have no more questions, I think we're done for today. See you all next week.